Dear students, in today's class we are going to discuss the third type of electron displacement effect, namely hyperconjugation. It's also known as Baker-Nathan effect. What is hyperconjugation? It is a permanent delocalization of electrons due to overlapping between a sigma bond and a pi orbital or a pi type or p orbital. Whereas inductive effect is delocalization of sigma electron, resonance effect involves delocalization of pi electron. Here hyperconjugation is a hybrid type. It involves both sigma bond as well as pi bond. It is a permanent delocalization of electron. It requires presence of alpha hydrogen. What is alpha hydrogen? Look at this example which we are going to discuss in detail, that is propene. Hyperconjugation is not shown by all types of molecules. It is shown by alkenes except ethene or some alkenes which do not have alpha hydrogen. Propene is the simplest alkene showing hyperconjugation. This is propene, right? Now this carbon-carbon double bond, with respect to this CC double bond, the next carbon can be considered as alpha carbon. This is one trivial method of numbering carbon. With respect to a functional group, the very next carbon is called alpha carbon, then beta, gamma, etc. So this is alpha carbon. Now hydrogen on this carbon can also be called alpha hydrogen. Now this is the structure of propene. It is shown with the orbitals responsible for pi bond formation. See, CH2, this is CH2, sp2 carbon, so it's triangular planar. This CH is also sp2, but this is sp3 carbon. Now this pi bond is formed by the lateral overlapping of these two p orbital, right? So this is a pi bond. We have shown the pi bond with the orbitals. So these are the pi orbitals you can call. Then the CH3 is here. Here these are the two sigma bond, and this CH sigma bond is shown in terms of the orbital. Of course, this is sp3 hybrid orbital of this carbon overlapping with oneness of hydrogen. So this is sigma bond or sigma orbital. These are pi bond or pi orbital. Let me take the model. Right? This is propene, carbon-carbon double bond. This is carbon-carbon single bond. Now, this pi bond, here there are two bonds, one is sigma, the other is pi. The pi bond is formed by the overlapping of one p orbital here and one p orbital here laterally, sidewise. So there is p orbital here and here. And now this carbon, which is alpha carbon, has 3 CH bonds. If you take one CH bond which has the sigma orbital here, now this sigma bond or sigma orbital is almost parallel to these two p orbital, right? These two p orbitals, and if you take this sigma orbital, almost they are parallel, so they can overlap. It's not very effective, but it is almost parallel and there is lateral overlapping possible. So this is what is hyperconjugation. Sigma pi overlap leads to a delocalization of electron along this orbital path. Since carbon-carbon single bond can be freely rotated, this is possible, right? Free rotation. So in the next point of time, it can be the next CH bond overlapping laterally, undergoing hyperconjugation, and again this also can undergo this kind of overlap. So this is hyperconjugation, overlapping of this sigma bond or sigma orbital with this pi bond or pi orbital, making a track for electron to move about. Hyperconjugation is not a very strong effect, but added together it can make a lot of changes in the properties of molecules. So in this diagram, this overlap is shown. Now on free rotation, it can be in the next point of time, this bond can come here and undergo overlap. So there are 3 alpha hydrogen here. So there are 3 possible hyperconjugative structures. Now you can see hyperconjugation. So this is a kind of conjugation, or this is a special case of resonance, because there is pi bond. Wherever there is pi bond involved, it will be a kind of resonance. So since this is a special case of resonance, we can draw resonance structures for this hyperconjugation. In terms of resonance, we can represent hyperconjugation like this. I am writing again this propene, right? CH double bond CH2. Okay. Now this is pi bond. So this sigma bond can be shown to delocalize into the next place like this, so that this pi bond will move to this carbon. Using curved arrows, we get the next structure as these 2 CH bonds are intact, and this bond is shifted, so hydrogen will be there without any bond, and it is losing this electron, so it will carry a positive charge. This becomes double bond CH, becomes single bond CH2, and this pi bond get localized on this carbon, so there's a lone pair and a negative charge. This is neutral, and this structure has 1 plus and minus, so it is totally charge is 0. So this is one hyperconjugative structure. Now we can draw as many structures as there are alpha hydrogen. This is one alpha hydrogen. We can draw another structure making use of this alpha hydrogen, this one. Then the structure will be like this. So we will keep these 2 hydrogen intact, and this is shifted. So H will be with no bond here, H plus, double bond CH, single bond CH2, and lone pair negative charge. We can draw one more structure because there is one more alpha hydrogen. When this is shifted, structure will be like this. Then these 2 hydrogens are intact, H with positive charge, double bond CH, single bond CH2, and lone pair. So there are altogether 3 structures, 1, 2 and 3 hyperconjugative structures. Since in these resonance structures or hyperconjugative structures, since there is no bond here between this carbon and this alpha hydrogen, this hyperconjugation is known by another name, that is no bond resonance. It's a special case of resonance. Okay. Now we will consider 2 more examples for hyperconjugation, or molecules in which hyperconjugation takes place. The second example is carbocations. Carbocation also exhibit hyperconjugation. Why? We will see that. Let's take an example, that is ethyl carbocation, that is CH3 CH2 plus. This is carbocation. This carbon is sp2. When it is sp2 hybridization, there will be one vacant p orbital here. So let us draw the structure of ethyl carbocation in detail. Single bond CH2 plus, and this carbon is carrying a vacant p orbital, right? So there's a positive charge, So because of this, it's clear obvious that this p orbital is a pi type orbital. So this p orbital can overlap laterally with this sigma orbital, forming a lateral overlapping. So hyperconjugation is possible. So we can now draw the resonance structures for this case. It will be shown like this. We shift this sigma bond to the very next place. We get the next structure as these two bonds are intact. This will be H plus because this bond is shifted. This becomes double bond and this CH2. There's a difference here. This is already carrying a positive charge and this is also having one positive charge. It is electrically balanced. Here there is no charge. This positive charge is delocalized or it is moved to this hydrogen now. Now the next structure will be making use of this alpha hydrogen. So it will be like this now. H plus double bond CH2. And the next structure will be making use of this alpha hydrogen. You will be getting like this. H plus double bond CH2. So here also we are able to draw 3 hyperconjugative structures. 1, 2 and 3. So 3 alpha hydrogen and so 3 hyperconjugative structures. More the number of alpha hydrogen, more the number of hyperconjugative structures, more the delocalization. Greater the delocalization, stabler the compound. That is a general rule with respect to delocalization. We have discussed in resonance that delocalization leads to stability. Okay. Now one more example we discuss, that is another class of compounds which exhibit hyperconjugation is free radicals. Because in free radical also there is a p orbital which is placed perpendicular so that it can overlap laterally with an alpha hydrogen or with a nearby sigma bond. We can take example again, ethyl radical CH3 CH2 dot, ethyl radical. This carbon is again sp2. Okay, so this carbon will be carrying an empty p orbital in perpendicular position. So lateral overlapping is possible here also. So hyperconjugation is possible because this p orbital is a pi type orbital. Pi type orbital means an orbital which can have a lateral overlapping. Let's take the structure of ethyl radical. It is like this, CH2 dot. So when you show the delocalization or hyperconjugation here, one difference is that there is one electron here. So in free radicals we make use of a different kind of arrow. What is that? Half-headed arrow. So we use a half-headed arrow or fish hook to show movement of only one electron. So what do you get? The next structure, this become like this. One electron is moved, so this hydrogen will be carrying one electron with it, but no bond. This become double bond CH2. So using this electron and one electron coming from here forms the double bond. You get the 2 more structures similar to that. Using this alpha hydrogen, structure will be now like this. H dot double bond CH2, and the third structure will be using this alpha hydrogen. It will be now like this, H dot double bond CH2. Here also we have 3 hyperconjugative structures. So these 3 class of compounds or species exhibit hyperconjugation generally. Now finally, on to application. What are the applications of hyperconjugation? In this context, we have only one example, one application to discuss. That is to compare the stability of but1ene and but2ene. Which is more stable? We can predict the stability of these two based on hyperconjugation. How? Let's draw the structure. But1ene is CH2 double bond CH, single bond CH2 CH3. Okay. But2ene is CH3 single bond CH double bond CH single bond CH3. Right. Now you can see that with respect to this carbon-carbon double bond, this carbon is alpha, this is beta. For hyperconjugation to exhibit, what is the condition? The molecule should contain alpha hydrogen with respect to the pi system. How many alpha hydrogen here? On this carbon there are 2 hydrogen, so 2 alpha hydrogens are present. You can draw the hyperconjugate structures using these 2 hydrogen as we have done earlier. Shifting this sigma bond here and pi electron will move to this carbon. You can draw 2 hyperconjugate structures in the case of but1ene. In the case of but2ene, look here, this is a carbon-carbon double bond. On both sides you have alpha carbon, right? And there are 3 hydrogen on each carbon. So altogether, how many alpha hydrogen? There are 6 alpha hydrogen in the case of but2ene. So you can draw 6 hyperconjugate structures in the case of but2ene. Here only 2 hyperconjugate structures. More the alpha hydrogen, more the hyperconjugate structures, or more the hyperconjugation effect, more delocalization and more stable. So but2ene is more stable than but1ene because it has greater amount of hyperconjugative effect. Okay, so this is the application we have to discuss at this point of time. You will find more applications of hyperconjugation in some other area. Similar to this example, we can see that if you consider stability of various alkenes, you can see that in the case of alkenes, when this carbon-carbon double bond get more substituted with methyl groups, for example, if this is CH3, this is only H, these 2 are hydrogen only, 1 methyl group, that means this is alpha hydrogen, there are 3 alpha hydrogen. If there is another methyl group here, then 6 alpha hydrogen, another methyl group here, 9, one more methyl group here, 12. So more the substitution on carbon-carbon double bond, more hyperconjugation and more stable the alkene. The point is, stability of alkene increases with more substitution on carbon-carbon double bond. Actually, this is the idea of sets of rule you might have learned in some your previous courses. What is sets of rule? During beta elimination reactions, more stable alkene will be the predominant product, in which case the more stable alkene is the more substituted alkene. It is because of hyperconjugation. Okay, so we wind up this discussion here. We have one more electron displacement effect in the coming class. Till then, bye.